Another important class of functions are what are called exponential functions. Now, generally, we would write this as a to the x with some base a. What we need to do is be able to figure out a formula for their derivative. If we were to just plug in this function into the derivative formula, we'll end up with an expression like this. If we were to sneak a peek, we would see 0 over 0. You can't use the limit laws directly. You got to do some algebra. Now, unfortunately, with the exponential functions, the algebra that we can do is limited. There's only one thing that is possible. We can factor out an a to the x from the top, and when we do that, we are left with this. Generally, once we hit the end of the road for algebra, we try to say, can I use the limit laws? In order to use the limit laws, we need to know if all the limits exist. The limit variable is an h. Anything without an h is considered to be a constant. So that a to the x is a constant. This thing contains h's. Does the limit exist? So later on, we will indirectly be able to show that this limit does in fact exist, and it equals the natural log of a. So it will exist as long as a is a positive number. So we are going to go ahead, apply the limit laws, and get a to the x as a constant times this limit. This is equal to a to the x times the natural log of a. So we end up with a nice little shortcut formula for this derivative. You can assume that this is fact from here on in, and you can just apply it. So for instance, if I give you that the exponential function is root 3 to the power of x, that means a is equal to root 3. And so according to the derivative rule, this would be 3 to the x times the natural log of 3. Now there is one very special case when this limit is equal to 1. That means the natural log of a is equal to 1, and that means that a is this special number e. That's called the natural base. So e is approximately 2.71828, blah, blah, blah. In terms of a picture, that says that the slope of the tangent line is equal to 1 at x equals 0. That means I would need to use the natural exponential. And because of this, we end up with a very special rule as well, that if we ever needed to take the derivative of the natural exponential, the natural log of e is 1, so the derivative of the natural log function is itself. So that is another very, very, very important rule. But this is not enough. All we've got are derivative rules for powers of x and derivative rules for an exponential. But what if I wanted to take derivatives of combinations of things? So what if I was given, 7 e to the x minus b over u, where b is a constant, plus 4 into the cube root of x. I should say x, not u. And so that's another important skill that we need to talk about. So these are what are called the linearity rules. Is it possible for me to take the derivative of a constant times a function? Is it possible for me to take the derivative of a sum or a difference of two functions? And the answer is it's definitely possible, but there's one thing you have to make an assumption. You have to assume that the functions f and g are differentiable. Because if they're not, then it really doesn't make any sense to talk about their derivatives. If I wanted to take the derivative of a sum or difference of two functions, according to the definition of the derivative, this would be f of x plus h plus or minus g of x plus h, subtract f of x plus or minus g of x. So I'm taking this entire thing within the bracket to be my function, and I'm using it there and there. As always, I would sneak a peek, get 0 over 0, no limit laws, but I would need some algebra. So the algebra here is going to be very straightforward. I'm going to assume that I can just split things up and reorganize. So I'm going to group together anything with an f, and it will turn out that the plus minus is a common factor for anything with the g. And what you're hopefully seeing is that things are naturally aligning into two separate derivative functions. Now remember, if all of these terms have an h on the bottom, then that h is a common denominator and essentially can be distributed to both. We are told this exists because f is differentiable, and this exists because g is differentiable. And that means I can use the limit laws. I can apply it to the first bracket, and then I can apply it to the second bracket, and I will end up with f prime of x plus or minus g prime of x. The derivative of a sum or a difference is the difference or sum of those two individual derivatives. So essentially, we can distribute the derivative to each term. That's very handy, because if I now wanted to apply all of the rules that I've learned, I don't have to develop something new. I can just apply all of the rules that I've learned little by little. So for example, if I wanted to take the derivative of 5 times e to the x minus 2 over x squared. These derivative rules say that you can split up a derivative of a sum as the sum of derivatives. Same thing with the difference. And if you have any constants, you can take out the constants. I could now write this as 5 times the derivative of e to the x minus 2 times the derivative of x to the minus 2. So the derivative of x to the minus 2 would give us x to the minus 3 with the negative 2 in front. So the linearity rules get coupled with the derivative shortcut formulas to make our lives easy.